Hello, everyone, and welcome to the Amazing podcast. I'm Twain Taylor, editor at Amazing, and we bring you some of the newest and the most innovative ideas in the space of cloud native and Kubernetes. So if your work and what you're building involves anything in this space, then you'll want to listen into each of our episodes. And go and check out all of the previous episodes we've done as well. We've been doing this for a while now. We've got a lot of conversations on different topics, everything from monitoring to security to networking. It's all in there. So you'll find something in there that's of interest to you. I'm excited to talk today to my guest, Rotem Tamir, who is the CTO at Ariga. That's Ariga, Ariga. And they're into database schema as code. So we'll get into what that means in a bit. But yeah, before we get into all of that good stuff, I want to start with saying hi, Rotem. It's great to have you with us. Tell us a bit about yourself and just your journey up to Ariga.
Great. Thanks a lot for having me, Twain. And as you mentioned, my name is Rotem. I'm 39 years old. For the past 4 years, I've been the CTO and co-founder of a company called Ariga. Our main effort is called Atlas. Atlas is a database schema-as-code tool. So kind of a modern DevOps take on how we should manage database schemas. We'll get into that a bit later. I've been coding since I was a young kid, and in the past, I guess, decade, mostly centered around what's gotten the name now, platform engineering, DevOps, building tools for developers. So always loved coding. When I started working professionally, I learned that it was not as fun as just programming, but I guess my career is about closing this gap, making good tools for developers, making it more fun and manageable.
All right. Really interesting. So yeah, database schema as code, that's a mouthful, but I think the key word there is schema. And I want to get us started talking about just that term itself. What is a schema? Why is it important? How is it used? Could you give us a lowdown on just this term, schema?
Perfect. So if we're writing backend applications, and so we have a server component, and then we have some component needs to store the state, the data. This typically is some form of database, and this varies a lot because there are hundreds of types of different database engines, but most likely our listeners are using some form of relational database, something like PostgreSQL, Microsoft SQL Server, MySQL, even SQLite today used in production. So these relational databases basically organize the information into tables. Tables are built of columns and have all sorts of other objects surrounding them, like triggers and functions, stored procedures and indexes and all sorts of stuff. So we typically call the shape of the database the schema. I think it gets the name from, in the database metadata layer, this is called the information schema, basically the part in your application that describes how the data is organized in the database and all of the relations, rules, triggers, constraints that come along with that. Its importance is that typically the value that is generated from applications comes from processing data. And the difficulty with this part is that it must evolve over time. So we know that software is never done, and we have built pretty elaborate machinery to push out software updates. If we build a new binary, we can wrap it in a Docker container, and we have this Kubernetes cluster that can get the new version, connect it to the load balancer, do all this stuff automatically. We need similar machinery to take care of the database, because contrary to applications, databases, you cannot just throw them out, put the new version connected to a load balancer. You need the data to persist over time, which presents a lot of challenges. That's why we are here and what we are trying to solve.
All right. Wow, really interesting. Another word that comes to mind is metadata, but that's probably more in a non-database context. But it sort of sounds like there's a layer on top of the data itself, which kind of acts like a map, you would say, to the underlying data and helps you process and analyze the underlying data quicker. Would that be a layman way of explaining it?
So the schema is basically the shape, right? It's what if I have a user entity in my data model, and this user entity is stored in a table. This table has columns like a primary key ID of type integer 64, and it has a first name field and a last name field. Both are text fields, text columns, and I have an index on the first name because I want to do lookups faster. So this instructs the database what the shape of the data is and how to store and access it on this. So this kind of creates the API between the querying application and the storage layer. And the valuable thing about it, when you think about it as metadata, is that once you have this kind of defined in some formal or structured way, you can start doing all sorts of interesting stuff with it programmatically. So for example, we know today that usually our data is not stored only once. We take it from our online Postgres database and then stream it somehow to a data lake or a data warehouse. The shape of the data that's in the original database really matters to the downstream consumers. So if we have some way to express this as metadata, as some data object we can handle, describe the database, we can also do all sorts of cool stuff about it. So it's on one side, it's metadata, it describes the data, describes the information, but it's also the concrete instructions to the database, how our application behaves and how our data is stored.
Right. All right. Neat. And in terms of use cases, right? I was wondering, you mentioned some of the relational databases as examples. Is there a place for schemas in non-relational databases as well? And apart from that, you also mentioned it primarily being used in backend applications. Could you give us some examples of real-world use cases of those kind of backend applications, and even what probably kind of use cases that where a schema wouldn't really apply, to just kind of set some
Sure.
context?
Great. So if we try to kind of on a high level look at various types of software that we generally call databases, but really they're very different from one another. But let's say they are containers of data and they have some standard way of storing and querying. So if we look at key value stores like Redis, then the schema is typically handled in the application layer. So maybe we're storing some JSON or some protobuf or whatever we choose. Typically, the encoding decoding happens in the application, and the database would be oblivious to. It's just a blob to me. On the other extreme, right, we have relational database where data is completely structured. And in the middle, we have the whole range of NoSQL databases, which have various degrees of schema-ness, call it, right? In Elasticsearch, you can store any kind of document, but you can define a structure for an index, which kind of sets some expectations and rules about a specific group of documents. If you look at storage like Cassandra or ScyllaDB, then it's not exactly a relational database because the query engine works differently, but still you're talking about tables and columns. So it really varies on the storage technology and the use case, but I think we've learned this over the past decade that schemas and static typing, having clear data contracts is really important. As software becomes more complex, it's really important to have the contracts well defined. And when the database supports that, we have a lot of benefits.
Mm-hmm. All right, all right. Oh, really interesting. So in terms of schemas, creating and managing them, what's been the story so far over the past few years? What were some of the traditional options for creating and managing schemas, and how have they evolved? And kind of pretty much like what was the need for a solution like Atlas?
Great. So I'll give a bit of history, and then I'll describe my own like personal career and pains that led us to build Atlas. So the database has always been like the core part of any enterprise application. And like if you look 30, 40 years ago, you would have this person, this role called the DBA. Sometimes it was one person, sometimes it was a full team. And because the database was so important and vital and precious, you had a software engineer or a specialized engineer whose role in the organization was to take care of the database. Now, this typically would also encompass managing the database instance, its upgrades, taking care of the whole thing. A lot of that today is offloaded to services, to manage cloud services like RDS. But still, you had the core responsibility of maintaining the tables, taking backups, really understanding how everything is supposed to work, and also optimizing. So helping application developers optimize queries, helping to think about optimal table layout to help the database engine do a better job. And DBAs had lots of tools built for them. So some of it was like vendor supplied GUIs or just use a terminal shell to interact with the database and issue commands. Now let's add an index on this column, or show me the metadata about this specific table. And we had this kind of combination of point and click interfaces and just raw terminal access. Because this is pre-microservices, pre-cloud, we had one big enterprise from Oracle, SQL Server. This was something that was done by a team. If an application team would need a change, they would create something parallel to a support ticket and ask the DBA team to take care of it. In the early 2000s, when we started hearing about DevOps and the importance of automating software delivery, we had a class of tools that we today call them classic migration tools, schema migration tools, that were created in order to automate the delivery of database schema changes. As we described earlier, software is never done. We want to ship a feature before we deploy a new version of our backend. That new version is going to rely on some table structure. So we need to modify the database before to add this table or add this column. So we typically, our deployment sequences, we have to deploy the database changes before we deploy the application changes. And we needed some software to automate that. And the name for transitioning from a previous version of the database schema to the next earned the name migration, because we are migrating from old version to a new one. We could have just as well called them upgrades or deployments, but that's kind of the industry term. So around the mid 2000s, so I believe 2006 to 2011, some of these tools were created. Famous names are Liquibase and Flyway. And the way these tools work is that basically the developer is responsible to define a migration script. So a set of SQL commands that can be defined in Java or XML or a bunch of other syntaxes, but essentially to describe in a script the commands that need to be run. And then we use the tool to run these commands in sequence. The tool stores some metadata on the target database to remember which scripts have run. So we know how to go from, we know that the database is at version 4, and now we need to apply 5 and 6 to come to the most recent version. And typically these tools also require the developer to plan the down migration, so the inverse operations. If I'm adding a column, then I need to define the removal of that column in the down script. And then I can, if I need to go back, then I have that all taken care of. And following this paradigm, over the following 15 years, hundreds of tools in this spirit were created. Many of them are shipped with the ORM or application development framework. Some were kind of language independent or framework independent tools meant for automation. But we have today in the industry several hundreds of these classic migration tools, and they all follow the same idea. When you want to make a change, you need to write a script, you commit it to source control, and then you run your scripts using a tool during deployment. The tool is responsible to check what scripts we have already run and run the missing ones in sequence, and that's it. So that was a situation on the ground until a few years ago. And when we started the company, we had actually a bunch of other ideas like all startup founders, but we released Atlas because we saw something very interesting in our own career paths that as kind of platform infra engineers, we saw the industry go from managing cloud resources in a point and click way to using scripts to using infra as code tools like Terraform and managing containers declaratively using Kubernetes. And we were working around a bunch of problems that were supposed to help people get more out of databases. And then it hit us that really that it should be possible to deliver something like Terraform or like Kubernetes, but for the database schema migration path. And when we released Atlas initially, we released a very small release to users of some other open source project that we were maintaining just to get feedback, and we got like Hacker News front page by accident. We really weren't ready for it, and I sometimes go back to read this thread because a lot of it is people saying, yeah, this is a really great idea, we'd love this for this to happen, but practically it's impossible. It's too difficult of a technical problem. I would never use something like this. So a few years later, I can say that this is a lot of this. When you tell a software engineer that something can't be done, they typically, don't accept that as face value. And we worked very hard, and we can maybe discuss some of the problems. Yeah.
Oh, interesting. That was quite a detailed and really interesting way to present just the story of, how database versioning is just such a gnarly, difficult problem to solve. And that's what was like gave rise to something like Atlas. So yeah, versioning, and I love how you describe the change from point and click to scripts to declarative. Yeah, that's quite an interesting way to think of all of this. So yeah, so versioning is like the most difficult thing to like do in terms of managing the database. But what are some of the offshoots of this challenge? What are the other because of versioning, what are some of the other challenges that organizations face in terms of like their applications, how they run them, some of the compromises they need to make? What happens?
So the problem, the database presents a unique problem to software delivery teams or to teams building software because of its critical yet stateful nature. If you have a problem with compute, you can typically roll it back. It's a stateless component. You can throw out the new version, redeploy the old version. Things will probably work out. But when you change the database, things are more tricky. One, because of it's a stateful component, so some changes are not legal, right? There are constraints when it comes to data. For example, if you want to add a unique constraint to a column, if that column already has duplicate values, this might work on your empty staging database or locally when you're just developing against an empty copy, but this might fail mid-deployment, right? So if you're not careful, you can drop the wrong column, run the migrations against the wrong database, find yourself in a situation where you've lost data. Now you need to come back from a snapshot. That's something most teams are not like really well practiced in how to do. Sometimes they discover the most recent snapshot is 24 hours old, and now they have a hole in the data. So lots of problems, and we've interviewed hundreds of software engineers around database schema changes over the past 4 years, and I think everyone has had at least one like big incident, big outage related to a data schema change, that database migration that didn't go so well. And so what we found happens is that people get really kind of defensive, or really try to avoid making database schema changes as much as they can, which is really a shame, because schema changes are a form of refactoring, right? If you would think about this in a source control, if there was a typical, a very common type of change that would really help you stay nimble and refactor your application, but you couldn't do it because you were afraid, like that's why we created unit tests, right? So we can repeatedly get confidence from the system that it's not broken. But with databases, it's more difficult. So you have all these teams basically avoiding change, saying that any change needs to be reviewed by the most senior, engineering function, need to spin up a copy of the database, make changes really, really expensive. And we know that if we read like DevOps professional literature, we know that the whole idea of the DevOps movement is to reduce the unit economics of making change really cheap. So the database had this problem, right? So you want to move fast so you can, iterate on your product, but you really want to move slow because you can't afford database downtime. So Atlas kind of fits in the middle there, right? And basically we think about database migration software as automation, but if you really look at the life cycle, you see that they're pretty manual process, right? You want to start a change, so you need to plan it. Who plans the change? A human, right? You create a pull request, it needs to be reviewed, needs to be validated. Who makes sure that the pull request is safe? A human expert, by the way. The most expensive resource in the company typically is the time of the senior engineering leadership. Okay, now it comes to times to deploy, right? We have automated deployment machinery that really is automation. And post-deployment, there's the whole issue of monitoring the system, detecting drift, making sure that there are no manual changes. We are always in this expected state. And if you look about this like really manual process, the goal we set was to bring the Terraform level, or even better than Terraform, because the API surface is much smaller than all of the cloud resources in the universe, to make something really, really excellent. So the experience we want is, I'm a developer, I make a change to the desired state of the database. Basically, I describe my database schema as code. I can do it in SQL, I can do it in Python, whatever language that we have adapters to all sorts of representations. And that's it. My work is done. I create a pull request, the change is detected, it's automatically planned, it's automatically verified. We've built a static code analysis engine that understands the semantics of change and can surface this. And this change on this version of Postgres that you're running is going to lock this table. If it has a lot of records in it, then it might be like an outage. Are you sure that here's an alternative way of doing it? So we have the analysis phase. We have all the integration with GitOps or infrastructure as code machinery. So it's not like this orthogonal part of your application deployment. It's just one more resource that we're managing. And yeah, so those were like the product / engineering goals that we had building Atlas.
All right, yeah. I want to get into like a little demo of Atlas in just a bit. But is there anything more you'd like to add? Because you've already given us kind of the context and kind of the principles of why you and how you built and designed Atlas. Is there anything more that you'd like to add to that in terms of like what makes Atlas unique, or some of the features you guys have been working on, or would you like to just go to the demo right away?
So I just came back from Salt Lake City from KubeCon, and there I presented something that I think is just worth calling out, because something that like we went really deep into and learned about in this journey. It's the topic of rollbacks, right? Rollback is the undo button for software engineers, right? If we make a change, we want to be able to undo it in case we need to. And the classic migration tools give us some false confidence because we have this supposedly this down migration pre-planned. So if we need to, but we talked to hundreds of software engineers, as I mentioned, and we discovered nobody uses them, and it gives us some false confidence. And in the talk, which I'm happy to share in the show notes later, we go into all of the reasons, but we can like mention one thing, which is the if you need to pre-plan what you're going to do in a failure, it's kind of a weird situation because the assumption that you make when you're planning the reverse operation of whatever change you're rolling out is that everything succeeded, right? So if you add a column, then add another one, the down migration is going to be drop both of them. But what if the first one didn't go through? That's exactly the situation where you want to roll back. So you kind of very naively and optimistically plan the down operations based on the assumption that everything passed. But realistically, when do you need to undo stuff when stuff goes wrong? So we really think that you need a declarative approach, something that can analyze the state of the database and figure out a concrete way to take this specific database, not some theoretical database at some theoretical state. So we really think that it's not just like about developer experience and easier, less hassle, save you time. It's really about correctness and about delivering something that can truly automate the process and not rely on manual operations too much.
Really interesting. I was wondering if you could give us a quick demo of Atlas in action.
Sure. Yeah, I would love that. Let me just close some of my tabs just so things are not too bad. And it will take me one more minute. Great. So I'm going to demo what this declarative flow for schema changes. So the whole idea with declarative is that we don't describe migrations, we just describe the state of the database. And here we have some, users table and post table. The schema here, by the way, is composed of both Python code and SQL code. So you can mix and match building blocks from different programming languages into one schema representation. And when we want to make a change to our schema, our only job as developer is just to change the desired state. Okay, so we change the schema here. We create a new pull request, and as developers, that's it. Like our job pretty much is done. So in a typical workflow, what we would now need to do is we need to plan the migration, we need to simulate it on some database, we need to bring someone in to review our changes, but we can see how Atlas saves us all of that. So what I have here is a GitHub action, and this GitHub action is running some prepared action that we publish that installs Atlas on the GitHub runner, and then it runs a command called schema plan. What schema plan does is basically go to my target database. I'm here running a Neon Postgres serverless database, and it compares the desired state, which is described in my SQL and Python files, with the current state of the database. Okay, and what this does is produce a plan. The plan is the set of sequences that need to be run in order to reconcile between the current and desired state. Okay, once this finishes running, what I get as a developer is a comment on my GitHub pull request. So you see that Atlas detected the changes to the desired schema. The changes are very simple: to modify this table and add this text column. And also what Atlas does is that we call this linting, but it's really analyzing the changes. So in the background, what happens is Atlas spinned up a temporary Postgres database. It brought the schema to its current state. It replayed this new plan on it, and it did all of this analysis stuff to make sure that the changes are safe. Okay, so once I'm good with this, I'm going to merge this. And what's going to happen now is that this change is going to go into something called the schema registry. Okay, schema registry is this component that we have that is kind of like a Docker hub for the schema changes. So you can see whenever the database changes, we have a version. We can compare between the different states. Okay, and we also have these plan objects that are stored here in the registry. So Atlas basically remembers this specific plan of adding the column, and when we deploy, we can set it to only execute plans that were pre-approved. So we also can get this confidence that only the changes that we saw in the pull request phase are going to be applied on the target database. So my whole job as a developer is just to change what I want the database to look like, and Atlas pre-plans, automatically verifies. The deployment can be done with a Kubernetes operator, with Terraform provider, just as a CD pipeline for my GitHub Actions. And so it's end-to-end automated.
All right. Wow. Yeah, that's a great quick demo of the developer experience there. What about for the ops side? What do platform engineers most frequently do? Do they mostly look at the maps that you showed in the Atlas dashboard? What do they do there?
So platform teams typically come to us for a few reasons. The prime one is they have adopted the Kubernetes GitOps mindset, and now they're looking for a kube native way to integrate schema changes as a resource within their whole infrastructure. We define everything in Kubernetes with crossplane and operators and everything. So we have a Kubernetes operator that kind of wraps the database schema as a resource and lets you do the whole Argo CD, Flux CD, whatever you're doing. So teams come to us because they're looking for that component. How do I do this in the Kubernetes native way? The second reason that platform teams come to us is because there is diversity in their development stacks, right? They're using Rails and Django and Hibernate and Prisma and 10 different ORMs, but they want one standard tool, one standard interface that can understand all of these different representation or frameworks, but still allow them to do stuff like governance, define rules, have a standard CI/CD pipeline for databases, so they don't have to deal with all of these complexity. These are platform teams that understand the schema management is not an application development problem. It's something that should be part of the company kind of golden paved path. What do we supply teams to move faster? And Atlas works well for them because we have adapters to all of these ORMs, and then they have all of the databases on one side, all of the languages on the other side, and Atlas acts as this middleman to provide a standard interface. And the last thing is the control plane, right? So if you are managing hundreds of databases with dozens of microservices, it's very beneficial to have one system track each deployment and to have this thing logically and semantically aware of the concept of schema changes. So if something failed, we can drill down to the specific one and see everything connected, the pull request, the CI run, the specific logs, have some remediation advice. It's very useful to have schema drift detection. So we have this agent that polls the database schema, checks that if there are any unknown objects or any missing objects, you could get an alert. So the platform team typically benefits more from the control plane, from the standardization story, whereas for application developers, it's mostly about productivity and kind of offloading this annoying and old problem to a tool.
All right. Wow, really cool. Last couple of questions for you, Rotem. The one that came up while you were even explaining just the platform engineer's role is just standardizing things and even keeping track of changes. The word that comes to mind is compliance. And I wanted to just ask about, how are schemas relevant to compliance? How do they help organizations be more compliant? And even Atlas itself, how does it approach compliance? What does it enable?
Perfect. So compliance is a huge part of all of our lives today. I think as software developers, very different from the world where I started coding at. Even as today Ariga is a 15-person startup, we are SOC 2 compliance, and we need to deal with this stuff on a daily basis. So database schemas and database schema changes are relevant to compliance in two vectors. One is the requirement of change management. So most compliant frameworks require you to show that every change to your production environment will initiate in some request, some Jira issue or GitHub issue, that it was introduced via a pull request that was reviewed and that went through some automation to verify that it's safe, and that was deployed automatically. So basically, Atlas gives you all of this lineage, right? You see the change, you see the pull request, you see the automated review, you see the deployments, and you see the schema monitoring, then closing the loop and proving that everything is hermetic and that there are no manual changes to the production system. So from a compliance perspective, this is just like export CSV, and you can get this compliance proof to show that all of changes to your database are done in a compliant way, and your change management for the database is well managed. The other perspective that bothers people, or because of privacy laws and kind of GDPR style legislation, is that companies rightfully are required to keep track of personal information, health information, sensitive data of their data subjects. So if I'm managing data for you, I need to really know where in my system I'm storing this type of information, to the point where governments can come and audit you, and you need to be able to prove that you did every effort you can to keep track of this, and you have some program to show that if you need to delete data or you need to present it somehow, you're able to. And one of the places where this metadata is relevant is, of course, the database schema. As we said, the schema describes the shape of the data, and who better than the developer to annotate the column if it is supposed to contain, MAC addresses, because the person writing the application has the most context. So for Atlas, this means being able to add metadata to schemas, so annotations, like who is the data owner of this entity, or does this entity contain information relevant to some compliance threshold, and being able to enforce this in CI or in monitoring, basically to allow the platform team or the compliance function to define these rules, and then make sure that development, we are constantly aware of where we're storing this sensitive data. So I think data privacy, all of this stuff is really, really important in this world that we are living. And the database schema is this centralized place that has a lot of potential to improve our abilities around this stuff.
Yeah, we're almost out of time. And the last question on this topic of database management that I want to ask you is just a word on just where we're headed, what's next. You guys have built Atlas, and this is, and you reached a certain point of, a different approach to just these challenges that we just spoke about. But what do you see as the next big thing that's coming up in, let's say, the next 1 year or so for either for Atlas or for just the industry at large, just database management?
So I think that we are now 4 years into the company and 3 and something into building Atlas. Of course, it's built on a lot of research and prior work in this field, but I think it's very, very early days for us still. We have some very large companies using Atlas in production, lots of people in our open source community. But I think building something that kind of challenges the status quo for how to do something very core and fundamental to software engineering will take, I don't know, it's like a 10-year effort to make this change on the industry. And I think we are kind of reached this initial traction and success where we've proven that it works. We're proving that teams are willing to adopt it, but we still have a very long way to making it a standard. And making it a standard is difficult both from a market or industry education perspective, just lots of content appearing in podcasts and making people hear about and could consider the idea, see if it works for them. But it's also around solving a lot of use cases and lots of edge cases, right? So in the first year, you can solve like 80%, and then the farther down the edge cases you go, they become more difficult, and they become more rare, and thus more valuable to solve. But really, we have built, I think, something that really works for many teams, but still, in calls with customers, there's also stuff that we would love to develop and solve, whether it's like other types of databases, other programming languages, very kind of esoteric kinds of changes that only happen in very unique conditions. So I think we built like the foundations of the building, and now we're starting to really see it turn into something that can become a standard. So 1 year is very short in my perspective. I think it's a much longer effort.
Okay, yeah, and good luck with that. I think congrats on just your start and just the
Thank you.
distance you've come far. And
Thanks a
yeah,
lot.
we hope you'll come back and tell us whenever something big comes up at Ariga and you want to talk
Sounds
about.
great.
Before you go, Rotem, just a question that I ask all of the guests to get to know them a little bit
Yeah.
what's your alternate career path if not for your job in tech?
Okay. So I had one actually. I stumbled into this industry by accident. No, not by accident. I mean, coding since I was a kid, but my formal training is actually I'm a teacher. I have a teacher's diploma. And then, I kind of had this alternate reality where I studied education and informal education and history and all sorts of stuff. So I guess that's always an option if tech doesn't work out.
So teaching history is what you would most enjoy, you think?
I don't know if history is definitely interesting. But yeah, we're working with young people and maybe mix, like teaching technology, computers.
Oh, interesting. All right. With that, we come to the end of this conversation. And we hope you enjoyed listening in, listeners and viewers. And if you want to check out more, you can head over to ariga.io. That's the website to learn about Atlas. And do join us again for the next episode. We'll see you on that one. Take care. Bye-bye.